This video lecture will be concerned with complex numbers. The knowledge of complex numbers is a fundamental prerequisite for the analysis of linear circuits and for understanding their operation. Just a couple of examples showing why complex numbers are so important. The frequency response, which is used to describe the behavior of linear circuits, is a complex function of the angular frequency. Complex here has to be intended in its technical meaning, in the sense that the function itself takes values in the field of complex numbers. Phasors, that are used to manipulate signals in sinusoidal circuits, are themselves complex numbers. The frequency response of linear circuits and phasors will be defined and discussed in dedicated video lectures. A complex number z is a number that can be written in the form z equal to a plus jb. This symbol c is used to indicate the set of complex numbers. This other symbol means belongs to. In the expression of the complex number z, a and b are both real numbers. In particular, a is the real part of z, while b is called the imaginary part. Of z. The real part of a complex number z is indicated with the expression Re of z, while the imaginary part is indicated with Im of z. So in our case, the real part of z is a, while the imaginary part of z is b. The symbol j indicates the so-called imaginary unit. By definition, j is equal to the square root of minus 1. From this, we get that the square of j is equal to minus 1. Note that by definition, any complex number z can be written as the sum of its real part plus the imaginary unit times the imaginary part of z. Moreover, a real number c can be regarded as a complex number with imaginary part equal to 0. On the other hand, a purely imaginary number z prime is a complex number with real part equal to 0. Note that the imaginary unit is generally indicated with the letter I. The letter J is used instead in electromagnetism and electrical engineering because in these disciplines, I is frequently used to refer to the electric current. For this reason, we will always represent the imaginary unit with the letter J. We have defined a complex number as the sum of two numbers a real part and an imaginary part, which is still a real number, multiplied by the imaginary unit. This form of a complex number is also called the Cartesian form. The reason for this name is that the real part and the imaginary part of the number can be regarded as the coordinates of a point in a Cartesian plane. This plane, in the case of complex numbers, is called the complex plane or the Argand plane. The horizontal axis of the complex plane is called the real axis, while the vertical axis of the plane is called the imaginary axis. Of course, the real part coordinate is represented along the real axis, while the imaginary part coordinate is represented along the imaginary axis. So a complex number z can be represented as a point in the complex plane with coordinate a, the real part of the number, and b, the imaginary part of the number. The point in the complex plane is fully and univocally determined by the pair of real numbers a and b. This is actually not the only way to identify the point in the plane. For example, we might think of the point as the tip of a vector starting in the origin of the plane itself. In this case, we could determine the position of the point in the complex plane by measuring the length ρ of the vector, which is the distance of the point z from the origin, and the angle phi the vector forms with the real axis. The length ρ of the vector is called the modulus of the complex number, while the angle phi is called the phase of the complex number. A complex number represented through modulus and phase is said to be represented in a polar form. Modulus and phase are a pair of real numbers providing a representation of a complex number which is alternative and fully equivalent to the Cartesian representation. We will see that the polar representation is more convenient when the product or the ratio of complex numbers are involved. The Cartesian form of a complex number is more suitable for the sum or the difference of complex numbers. The Cartesian representation of a complex number is also called a rectangular representation. There is actually something more to say about the polar representation of a complex number. First of all, let us find out how we can transform a Cartesian representation of a complex number into a polar representation and a polar representation into a Cartesian one. Let us start with the transformation from the Cartesian into the polar form. So let's assume we have a complex number z written in Cartesian form. So z is equal to a plus jb with a and b real numbers. From the plot, it is easily found out that the modulus ρ, which is the distance of the point z in the complex plane from the origin, can be written as the square root of a squared plus b squared by application of Pythagoras' theorem. The phase phi, the angle that the vector forms with the real axis, can instead be written as the inverse tangent of the imaginary part divided by the real part. This result about the phase is actually true only if A is positive, so only in the case of a complex number with a positive real part. We will discuss about a more general definition of the phase, including any possible value for the imaginary part and the real part of the complex number, later on in a new video lecture. Note that up to now, in the case of the polar representation of a complex number, we have been using modulus and phase as a pair of real numbers, not integrated in a single expression as in the case of the Cartesian form, where the real and the imaginary part are combined together using the operations of sum and product by the imaginary unit j. We will find in a moment a very elegant and compact solution to express a complex number in polar form. Let us now consider the transformation from polar into Cartesian form. So let's assume we have a complex number z expressed by means of a modulus rho phase phi pair. By looking again at the plot and recalling the geometrical definitions of the sine and cosine functions, we can easily find that the real part A of the complex number z can be written as the modulus rho times the cosine of phi, while the imaginary part B of the complex number can be written as the modulus rho times the sine of phi. Note that based on the latter expressions for A and B, A squared plus B squared is equal to rho squared the cosine square of phi plus rho squared the sine square of phi, or rho squared times the cosine square of phi plus the sine square of phi. Of course, the cosine square of phi plus the sine square of phi is equal to 1, which leads to rho square. On the other hand, the ratio b over a is equal to rho the sine of phi divided by rho the cosine of phi, which is equal to the tangent of phi. These results are of course consistent with the rules for transformation from Cartesian to polar representation we have obtained before. Now we found out that the real and imaginary part of a complex number can be expressed as a function of the modulus and the phase of the same number as A equal to the modulus rho times the cosine of phi and B equal to rho times the sine of the phase phi. Now, according to the Cartesian representation of a complex number, z can be written as A plus jb, or, taking into account the expression of A and B as a function of the modulus and the phase of the complex number, cosine of phi plus j rho the sine of phi. Or eventually, if we collect the modulus, rho times the cosine of phi plus j the sine of phi. Now the cosine of phi can be written as a Taylor series as 1 minus phi squared divided by 2 factorial plus the fourth power of phi divided by 4 factorial, and so on and so forth. On the other hand, the sine of phi can also be written as a Taylor series as phi minus phi cubed divided by 3 factorial plus the fifth power of phi divided by 5 factorial, and so on and so forth. We can now replace the cosine of phi and the sine of phi with their infinite sums in the expression of the complex number z, and we get rho multiplying 1 plus j phi minus phi square over 2 factorial minus j phi cube over 3 factorial plus phi to the fourth power over 4 factorial plus phi to the fifth power over 5 factorial, and so on and so forth. Recalling that by definition the square of j is equal to minus 1, we can write the infinite sum between brackets as the sum for k going from 0 to plus infinity of j phi to the kth power divided by k factorial. But this sum is nothing else than the Taylor series for the exponential of j phi. So, in its polar form, a complex number can be written as the modulus times the exponential of the imaginary unit times the phase of the complex number. The formula e to the j phi equal to cosine of phi plus j the sine of phi is also known as Euler's formula. Given the use of the exponential function in its representation, a complex number represented through polar coordinates is also said to have an exponential form. To summarize, a complex number can be represented in the complex plane by using Cartesian coordinates or polar coordinates. In the case of the representation in Cartesian coordinates, the complex number can be written as a, the real part, plus j, the imaginary unit, times the imaginary part. The real part and the imaginary part are the Cartesian coordinates of the complex number in the complex plane. In the case of the representation in polar coordinates, the complex number can be written as rho the distance of the point representing the complex number from the axis origin times the exponential of the imaginary unit times the phase phi, which is the angle between the vector representing the complex number and the real axis. We can go from the Cartesian representation to the polar representation, remembering that the modulus rho is equal to the square root of a squared plus b squared, and the phase phi is equal to the inverse tangent of b over a. Again, remember that this is not, as far as phi is concerned, the whole story. We will discuss about the determination of the phase of a complex number later on in a new video lecture. We can go from polar to Cartesian representation by expressing a and b as a function of the modulus and the phase of the complex number as a equal to rho the cosine of phi and b equal to rho the sine of phi. Consider a complex number z represented in polar coordinates. So z is equal to rho a to the j times the phase phi. Let us assume that in this complex number, rho, the modulus, is equal to 1. This means that by definition, the distance of such a point from the origin is 1, whatever the phase phi is. Actually, by Euler's formula, we know that e to the j phi is equal to the cosine of phi plus j the sine of phi, where cosine of phi and sine of phi are respectively the real part and the imaginary part of the complex number. So in the Cartesian representation, they are the coordinates of the complex number z in the complex plane. So the distance of z from the origin, d, is equal to cosine square of phi plus sine square of phi, which is identically equal to 1, whatever phi is. Note that as phi increases from 0 to 2 pi, the point z in the complex plane moves along a circumference with unitary radius. This is also called the unit circle in the complex plane. Note also that both the sine and the cosine are periodic functions with period 2 pi. This means that the sine of phi is equal to the sine of phi plus 2n pi, where n is a relative number. The same is true for the cosine function. So cosine of phi is equal to cosine of phi plus 2n pi, again with n a relative number. As a consequence, also the exponential function of j phi is a periodic function with period 2 pi, which means that e to the j phi is equal to e to the j phi plus 2n pi. Now note that points on the real axis are purely real numbers, so complex numbers with imaginary part equal to 0, while points on the imaginary axis are purely imaginary numbers, so complex numbers with real part equal to 0. So a to the j times 0 is a point on the positive real axis with modulus 1, so it is simply equal to 1. E to the j pi divided by 2 is a point on the positive imaginary axis with modulus 1, so it is equal to j, the imaginary unit. E to the j pi is a point on the negative real axis with modulus 1, therefore it is equal to minus 1. E to the j 3 pi divided by 2 is a point on the negative imaginary axis with modulus 1, so it is equal to minus j. Of course, given the periodicity of the exponential function of a purely imaginary complex number, e to the j times 0 is equal to e to the j 2 pi. By definition, an nth root of unity, where n is a positive integer, is a number z satisfying the equation z to the nth power is equal to 1. If z is a real number, then z is equal to 1 if n is odd, is equal to plus or minus 1 if n is even. If z is a complex number, then recall that unity in exponential form can be written as e to the j 2k pi with k a relative number. Then the above equation can be written again as z to the nth power is equal to e to j 2k pi, from which we get that z is equal to e to the j 2k pi divided by n. Since the exponential function is periodic with period 2 pi, the only meaningful solutions for this equation are those obtained for k equal to 0, 1, 2, up to n minus 1. Outside of this range for k, the same solutions will show up periodically. So, in the complex field, which means if we take the roots from the set of complex numbers, the number of nth roots of unity is n. Consider, for example, the equation z to the third power is equal to 1. This equation has three solutions in the complex field: e to the j 0, which is equal to 1, e to the j 2/3 pi, which is minus 1/2 plus j the square root of 3 divided by 2, and e to the j 4/3 of pi, which is equal to minus 1/2 minus j the square root of 3 divided by 2. Of course, all the solutions are on the unit circle in the complex plane. As another example, consider the equation z to the fourth power equal to 1. This equation has 4 solutions in the complex field. E to the j is 0, which is 1. E to the j pi divided by 2, which is j. E to the j pi, which is minus 1. And e to the j 3/2 pi, which is minus j. Again, all the solutions are found on the unit circle in the complex plane. Find the roots of the equation z to the nth power equal to 1 for n equal to 5, 8, and 10. Find the roots of the equation z to the n power equal to 5 for n equal to 2, 3, and 4.